so we get the same results. So we say that the Euler test is passed. Hello guys, I hope you're doing great. In this video we'll be discussing exact equations. These are special differential equations which fulfill a particular criteria or a condition. These are equations which can be written in a particular format, and that format is, for example, you had 2x minus 5y dx plus minus 5x plus 3y square dy equal to 0. So as you remember that I told you earlier that in differential equations there will be instances where we will be considering y prime equal to dy by dx separately, that dy is taken as a variable and dx is also taken as a variable, and the rules of algebra which are applied on any variable are also applied to dy and dx. Just like that, we can write this down as 2x minus 5y dx equal to minus into minus 5x plus 3y square dy, and now I will be able to write it down as, I'm taking this dx to the other side underneath dy, so I will be able to write down dy by dx equal to 2x minus 5y divided by, and I'm taking all of this on the other side, so I get 5x minus 3y square, right? So I'm able to rewrite this as y prime equal to 2x minus 5y divided by 5x minus 3y square. So I have solved this thing in reverse just to show you that now it looks like something that you were familiar of looking at. If we go back, we get this equation. We have just written it in such a format that all the coefficients of dx are here and all the coefficients of dy are here. And as I said earlier, treating dy and dx just like variables and applying all the algebraic rules that we do on variables, right? So let's go further. Now this is the case that we have an equation which is written in this form. Let me call this thing a function m, which is a function of x and y, right? I'm just naming this function. All the coefficients of dx I'm naming as m of x comma y. Similarly, let me name all of the coefficients of dy as a function of x and y and of x comma y, right? So that will be the first step in solving exact equations. Is the first step. Let me write down as algorithm. The first step is write down the equation, write down first order differential equation as m of x comma y dx plus n of x comma y dy equal to 0, right? So that would be the first step. Now we go to the condition that is imposed on an exact equation, and that is that if that condition is fulfilled, we say that this equation is an exact differential equation. So step 2 would be, is it exact differential equation? Question mark. To check whether it's an exact equation, the test that we apply on this equation is called Euler's test. And Euler's test says that if this equation is, if function m of x comma y is partially differentiated with respect to y, and the second function, which is n of x comma y, it is partially differentiated with respect to x, and we get the same result, and let me put a question mark on top of this equal sign just to represent that we are checking for equality in this case. So if this check comes out to be true, that is curly over curly y m of x comma y becomes equal to curly over curly x of n x comma y, then this equation is an exact differential equation. So that means what we are getting as a result of both of these things is something which is same, which can be a function of x comma y both, right? So we get something which is a function of x comma y both, but it should be equal in order to satisfy that this equation is an exact equation. So let's first do an example. For example, we had an equation x square y cube dx plus x cube y square dy equal to 0, right? So what do we need to do? First, we recognize this thing as m of x comma y, and all of these variables we call n of x comma y. This is the first step. When we recognize both of these things, we need to take the partial derivative of the first thing with respect to y, and then we need to take the partial derivative of this thing with respect to x, right? So that will take me to the thing where I need to explain what is a partial derivative. A partial derivative is when you consider the independent variable of the partial differentiation as the only variable we consider a variable, and all the other variables we consider constants, right? So what do? We take curly over curly y of x square y cube. Since this differentiation is with respect to y, I am going to consider only this thing a variable, and I'm going to consider all the other variables a constant. So this is a constant in my eyes for now. So let me call, for the sake of explanation, let me just call x square a k, right? Just to emphasize that in this particular differentiation, which is with respect to y, a partial differentiation with respect to y, every other variable is just a constant. So I'm going to write curly over curly y of k y cube. So you know, when you take the derivative of a variable and a constant, the constant comes out of the product. So we write k curly over curly y of y cube. So the answer becomes k times 3 times y square, right? This is a standard derivative. Now let's put in the value of k back, and we get x square 3y square. So we can write it down as 3x square y square. Similarly, let's do the other part, which is that you have to take the partial derivative of this thing with respect to x, right? So the partial derivative of x cube y square with respect to x would be, we are going to consider everything which is not x a constant. So all of this I'm considering as a constant. So in other words, I can take it out of the differentiation. So let's do that. Y square into the derivative of x cube with respect to x, which is 3x square. So the answer would be 3x square y square. So here you see that the first factor is equal to the second factor, and which are 3x square y square. So we get the same results. So we say that the Euler test is passed, and this equation is an exact equation. Okay, so when we identify the equation as exact equation, now there's the time to solve it. One thing you should note over here is that if the equation is not exact, we cannot go further with this method of solution. We will have to employ some other method. So this method is only good for an exact equation. So that's why we did the Euler's test, for checking whether it was an exact equation or not. In order to solve the exact equation, first we start by understanding the definition of exact equation. The definition of exact equation says that we should be able to find a function f such that if we take the partial derivative of f with respect to x, we get m of x comma y, and if we take the partial derivative of this unknown function f with respect to y, we get n of x comma y, right? So when this is the case, we can see the exact equation in this way, that instead of m, I should be able to write curly f over curly x dx plus curly f over curly y, which is n of x comma y dy, equal to 0. Now our objective is to find this function f of x comma y, which is so far unknown to us, and we don't know what this function is. So finding the value of f of x comma y will be our solution. How can we proceed to find the value of f of x comma y? So the answer to that is that we know that curly f over curly x is equal to m of x comma y. So what if I took integration or integral on both sides? In order to take integral on both sides, first what we do is we take this curly x to the other side. So I write it down, curly f integral equal to curly m x comma y curly x. So we know that partial integration would be similar to partial differentiation, in which we will have to consider the variable which is being ignored, in this case y, because we are taking integral with respect to x. We will have to take this variable y as constant, right? So if we consider that variable y constant, this variable could have been lost during the differentiation when we landed on m of x comma y. So in order to make up for the fact that we are ignoring y, what do? Instead of the constant of integration, we will be writing g of y. This is an unknown function which is based on y, just to account for the fact that during this partial integration we are ignoring the variable y.